So today we're going to look at something that we saw last year, and that is heat transfer, or the escape of heat from a system that's at a different temperature than the environment. So the major idea that we saw last year was if we had a hot liquid inside this container, that heat would escape from the container until the temperature inside the container reached the temperature of the room. If the container was filled with cold liquid, heat would enter into the liquid until the liquid became the same temperature as the room. Okay, so that was our major idea. We saw this with our infrared camera, that heat would escape from our objects. So I had a container full of hot water. I poured it into a metal container, and you can see that the heat escaped from the metal container rather quickly. I then put it in a plastic container, you see the heat escaping less quickly. And then in a styrofoam container, you can see it escaping even less quickly. Okay? We saw the same idea with gloves. So when I took my hand and put it into a glove, we saw how the heat was escaping from my hand much quicker than it was escaping through the glove. That's the whole reason for wearing gloves, obviously. In terms of how does the heat move through the glove or the metal container or the styrofoam, our main method we looked at was conduction. And the idea behind conduction was that when you had a hot object, the molecules on that hot end would speed up. They would hit the molecules next to them. They'd transfer energies to their neighbor, who transfers it to their neighbor, and eventually the energy would move all the way through the material to the colder object. So conduction is when heat transfers by way of molecular collisions. It is a chain reaction where energy is passed from molecule to molecule until the heat eventually reaches the other side. In terms of the factors that determine how quickly the heat will go through a material, we had a picture like this, and I'm going to ask you to redraw this. We have a hot side and we have a cold side. In the hot side, the molecules are going to be moving around rather quickly, and in the cold side, the molecules will be moving less quickly. Again, we should think more of the kinetic energy will be high and the kinetic energy will be low on average. So again, the faster moving, the higher energy particles hit the wall. They transfer energy through the wall, and eventually that energy reaches the other container. This will continue until both objects have the same temperature. Okay? At that point, we will be in thermal equilibrium. But how quickly does the heat go through the material? It depends on 4 factors. It depends on the surface area available. Every piece of surface area, every square centimeter is another spot for heat to move through the wall. So a bigger area means the heat will travel through more quickly. So a larger area means a more rapid heat transfer. Thickness. The thickness of the barrier will have an inverse relation. So as you make the barrier thicker and thicker, the rate of heat transfer will become smaller and smaller. Okay? A larger thickness gives less heat transfer. The material is called the conductivity of the material, the thermal conductivity. The better it is as a conductor, the quicker the heat will travel through it. And finally, the difference in temperature. So if we had temperature 2 and temperature 1, and we subtracted those to get the delta temperature, the bigger the difference in temperature, the quicker the heat will transfer through. So those are the 4 factors: area, thickness, difference in temperature, and the material's conductivity. Okay? They all came together to form an equation that looked like this. Again, this side is giving us the rate of heat transfer. That's going to be measured in joules per second, or watts. How many joules pass through the barrier per second? It depends upon the conductivity, the area, the difference in temperature, and the thickness. The difference in temperature should be measured in Celsius. Remember, delta T could be Celsius or Kelvin. They're the same numbers, but Celsius is usually easier. The area should be in meters squared, and the thickness should be in meters. You should have on your reference sheet all your different materials. Higher numbers mean faster transfer. Lower numbers mean a slower transfer. Okay, so these are your conductivity constants, and they go by the letter K. Okay, and that's it. I just wanted to review some of the major ideas with you, and I'm going to give you one practice problem to make sure you remember how to use this formula. Good luck.